I'm Krishna Rao Patro. So today we will discuss about one important concept, that is properties of binary sets T. So in the previous session you have seen the binary tree concept. Now we'll see how the binary sets T is different from binary tree and how they are interlinked each other. Remember, this concept came from actually general tree. General tree means what? A nonlinear data structure where you can have a set of nodes, and a node can have any number of children. There is no restriction. So whenever you want to have a set of parent-child relationship, when there is no restriction on the number of child, then that is a general tree. So whenever you want to impose some condition, some restriction, for example maximum of 2 child, then in that case that tree become binary tree. And again in the binary tree, if you impose a condition, if the left child is always smaller than the parent and right child is always greater than the parent, then that tree become binary sets tree. And there is also one more tree called heap. Heap also one type of binary tree, whereas in the heap there is a condition. The parent either will be smaller than both the child or parent greater than the both the child. So when such type of property is there, that is called heap. And whenever left is small than parent and right is greater than parent, then that is called binary sets tree. So there is a difference between a heap tree and binary sets tree. But today we are discussing about only binary sets tree. So try to remember, in the case of binary sets tree, the left child always smaller than parent and right child always greater than parent. That is the condition. And if you can remember this condition, then you can identify what type of tree is. And if you observe this particular tree, a tree is nothing but what? Collection of subtrees. Whichever is on the left side of the node, means the left side of the node, that is called left subtree, and whichever is the right side, that is a right subtree. So I can say a tree is a collection of left subtree and right subtree. So in binary sets tree, left subtree is always smaller than the parent node and right subtree is always greater than parent node. So if you observe this tree, now please observe here, 10 is my parent node. On 10, there are 2 subtrees. One is left subtree, another is right subtree. In the left subtree, the values are 6, 1 and 8. And in the right subtree, the values are 13, 11 and 14. Now if you observe here, the left subtree values are less than parent, whose value is 10, and right subtree is greater than parent. So this is a valid binary sets tree. Whereas if you observe the right one, 10 is there, parent. Left side is having 6, 1 and 12. This 12 is what? A value which is in left side, but my parent value is 10. So it is not a proper one. It is invalid one. That's why it is not a binary sets tree. Similarly, if you observe here, right subtree, here in the right subtree, the values are 9, 13 and 14. Actually, my parent is how much? Parent is 10. So on parent 10, if you consider right subtree, all the data must be greater than 10. But here the value is 9 is there. So this 9 is not greater than 10. So it is invalid. So that's why it is an invalid binary sets tree. So most of the time, sometime in exam they may give a tree, such type of tree, and they will ask you find out which one is a valid binary sets tree or which one is a valid binary tree. Now, here this is a binary sets tree, whereas it is not a binary sets tree. They may ask a question, why it is invalid? Then you should say that because the right side subtree is having value more than the parent and left side tree is having less than parent. That's why it is. Now, if you consider this tree, now they may ask whether it is a binary sets tree or not. Now, if you observe here, 25 is what? My grandparent. And if you think this is a collection of left subtree and right subtree, complete left of 25, they are all less than 25. Left subtree values are less than 25. Similarly, complete right subtree of 25, they are all greater than 25. So all values which are exist left side less than parent, all values which are exist right side greater than parent. Now here value is 25. 25 is my parent node. Similarly, for every subtree also you have to check. Here if you think now 20 is my parent and 22 is right. So 22 is greater than 20. Similarly, left subtree of this, these are all less than 20. So for every tree there is a parent node, as well as there is a left subtree and right subtree. So every left subtree and right subtree should follow the binary search tree property. What is the property? The property is left child should be less than parent and right child should be greater than parent. This is the condition. If this condition satisfies, then you can say that tree is a binary search tree. So that property you should remember. Without that, it is impossible. Because most of the time in exam or in interview, they may give set of trees. They will ask whether it is a proper or valid binary search tree or not. Or they may ask, find out which subtree or which tree is a binary search tree also. Now they may ask where the binary search trees are useful, where exactly you can use in your day-to-day life also. Binary search trees are useful for indexing as well as for multi-level indexing. So whenever you are storing lot of records, so you need indexing. So with the help of the indexing, you can set the record very fast. So for indexing purpose, you can use even the binary search tree. Similarly, they are also useful to implement various searching algorithms, because generally searching is one of the important operation. If the data is arranged in a proper way, then searching can be take less time. So if you implement binary search tree, or if you organize with the help of the binary search tree, then searching will be very fast. So for searching purpose, binary search tree can be useful. Similarly, it is also helpful maintaining the sorted stream of data. For maintaining sorted stream of data, binary search tree can be also useful. And there is one more important application where generally tree map and tree set data structure, especially in the advanced language like Java and all, they are using this data structures. There binary search tree is used. So using binary search tree, you can implement this tree map as well as tree set data structure. So a huge collection of data can be organized in a simplified way and which takes less time. Now, what are the operations are allowed on binary search tree? Generally, the operations like insertion, deletion, traversal, searching, these are the common operations in any of the data structure, whether it is a linear data structure or whether it is a non-linear data structure. So, our binary search tree comes under non-linear data structure. So, there you can apply the following operations. First one is what? Searching. Searching operation performed on a binary search tree with order of log n complexity if it is fully balanced. If the tree is balanced properly, then it is order of log n time. But if the data goes in a sequential way, then that become order of n. If it is in a sequence. Okay. Next, insertion. Similarly, the insertion operation is performed with order of log n time complexity because it is arranged in a balanced way. So, in a balanced binary search tree, when you are inserting data, it will take order of log n time. Similarly, in the deletion operation also, it takes order of log n time because it is a balanced one. Balanced one means either go left side or right side. At a time, you are deciding either left half or right half. So, whenever the divide and conquer policy comes, always the time complexity will be in terms of logarithmic series, log n. Because here, binary search tree always keep the data in a divide and conquer policy. But only in the rare cases, if the data goes in a complete one side, there it will take order of n. Because if you store the data in a sequential order, that will become a linear data structure. Now, There is another operation called traversal, because traversal is one of the very common operation in a binary tree, because traversal will help you to traverse the entire elements of the tree. So there are three types of operations, means standard types of traversals: in order, pre-order, and post-order. As well as one more additional is also there, that is called level order. So these operations you can apply on traversals. So they are the common operations on binary search tree. First we will see the insertion operation. How insertion can be done in binary search tree. So whenever you want to insert a node, first of all you have to check whether your root is empty or not. Because for every tree there is a starting point. The starting point of a tree is called root. If no elements are there in the tree, then the root is always null. So that is represented by empty symbol, by null symbol. So you have to check, because whenever you want to insert a node, you have to first check whether you are having any elements in the tree. So how will you know? By checking the root. If root is null, it says it is empty tree. So step 1, create a new node with a given value and set left and right is null. So first of all, you create a node with value, assume some 10, and put left null and right null. Because for every node of a binary tree or binary search tree, there will be three parts: data part, left child, as well as right child. So initially, when you are creating a node, you do not know whether you are having left child or not, or you do not know whether you are having right child or not. That's why initially the node's left child as well as right child will be null. That's why in the first step, create a new node with a given value and set its left and right null, because you are not aware of whether you are having left child or right child or not. That's why for every node you put a null first. So after creating the node, then check the tree, whether tree is empty or not. If tree is empty, it says first time you are creating. In that case, this starting node itself is a root node. So if tree is empty, then set that new node to the root. That become root. Otherwise, if already some nodes are there, in that case what will happen? You have to decide whether this node will be either left of the root or right of the root. That depends on the value. So I told you already, if the data is, new node's data is less than the parent node, then go left side. If the data is greater than the parent node, go right side. That is the policy. So in the step 4, check whether if the tree is not empty, then check whether the value of new node is smaller or larger. So based upon the value, it will decide whether to go left side or right side. So check whether smaller or larger than the node. So in the step 5, if new node is smaller than or equal to the node, then move to the left child. So the new node will be acting as the left child of the parent. If the new node is larger than the parent node, then move to the right child. So that means this new node become right child of the parent. Then step 6. Repeat this above steps, because there may be, you may insert for multiple nodes. Repeat the above steps until you reach the leaf node. Because if already some nodes are there, then you have to check whether any nodes already exist or not. If already node exists, then go down. So you have to go till bottom. That means whatever the node you are inserting, that will be always acting as a leaf node. So the new node, whatever you are inserting, that will become a leaf node. Leaf node means the node which having no left and no right child. That's the dead end. Now step number 7. After reaching the leaf node, insert the new node as a left child. If the new node is smaller than or equal to the leaf node, or else insert a right child. So based upon the value, you have to decide whether left side or right side. So this is the 7-step process to insert a node in the binary search tree. So these steps you have to follow while inserting a node. Now let us construct a binary search tree for the given data. Now if you observe here, the given values are 8, 3, 10, 1, 6, 14, 4, 7 and 13. This is the given value. Now, because most of the time, even in the exam also, they will ask construct a binary search tree, construct a binary search tree for the given data. So, how will you construct a binary search tree? So, when you are giving this type of data, always you take the first node at the first data. So, that means 8 is the parent node or root node. Next comes 3. When 3 comes, because initially 8 came, now 8 become my root node. After root is created, then the remaining data you have to decide whether left or right. Based upon the order of the data. In which order you have given data, that will decide the tree. Because if the order changes, automatically tree also changes. So you have to follow the given sequence. So the next data is 3. Now if you insert 3, which side you have to insert? Please observe here. Because 3 is less than 8. So it should be left of 8. So 3 is inserted left of 8. Now next data is 10. Now where you have to insert 10? Always you have to start checking from the parent. So here by root. Here root is 8. And my incoming data is how much? 10. So always start from root. Now 10 is greater than root. Yes. So that means I have to insert the 10 on the right side. So insert 10 on right side. So now, till now, 3 data. Now next is 1. Now when you want to insert 1, where you have to check? Always start from root. So 1 is less than 8. So come to left side. Now the left side already data is there. That is 3. Again 3 become the parent. So 1 is less than 3. So 1 will be left of 3. 1 will be left of 3. Yes. Next is 6. When the next data is 6, you have to check where you have to insert. Because you have to check from always root only. Now my root is 8. 6 is less than 8. So come to left side. But after coming to left side, already 3 is there. So but 6 is greater than 3. So come to right of 3. So 6 is inserted right of the 3. So this way you are inserting this. Next is 14. So when 14 is coming, you have to start checking from root. 14 is greater than 8. But already on the right side of 8, already 10 is there. So now 10 become parent. Now 14 is greater than 10 or less than 10. 14 is greater than 10. So right side. Come to right side. So right side of the 10 inserted. Next 4. When 4 is coming, 4 is left of 8, greater than 3, less than 4, so 8. So 4 is inserted here. Left of 6. Because always you have to start checking from root level. From root you have to decide the path, whether left or right. After coming there again, in that subtree's parent you have to check whether left or right. So always there are 2 root, either left or right, based upon its value. Next is 7. 7 is greater than 6, so right. Next is 13. Now you observe 13, where 13 will be inserted. Because you have to start from checking from root. 13 is greater than 8. So come to right side, but 10 is already there. Now you have to compare 10 with 13. 13 is greater than 10, right side, but already 14 is there. Now 13 is less than 14, so left of 14. So 13 is inserted. So this way you can construct a binary search tree. Once the tree is constructed, now they may ask a question. There are different traversals are there. After constructing the tree, they may ask in-order traversal, pre-order traversal, as well as post-order traversal or level order traversal. There are 4 different types of traversals are there. What is the value of this? If I follow in-order traversal, the in-order says left, root and right. That is the in-order traversal. That means 1, 3, 4, 6, 7. 1, 3, 4, 6, 7. Left subtree. Then the root. Root is 8. Then right subtree. Right subtree is again no left, root 10, then right subtree 13 and then 14. So this is my in order traversal. Even in recently in one of the exam, they asked the question, what is the level order traversal? The level order traversal is very easy. Remember, level by level. So this is the first level, this is the second level, this is the third level, this is the fourth level. So level by level simply you have to display. So they will give the multiple choice, which is the correct level order traversal for the given tree. And moreover, they will not give the tree also. They will give the set of data. You have to construct the tree. From that tree, you have to find out the level order. Now, if I ask the level order, what is the answer? The level order answer is, first is 8, because first level, then 3 and 10, 8, 3, 10, first level, second level, third level. Third level is 1, 4 and 14. 1, 4 and 14. Third level. Then come to fourth level. In fourth level, 4, 7 and 13. So this way you can display the data. So most of the time they ask this type of question. So you must be ready for the how to construct a tree. Once the tree is constructed, then you can do all in order, pre-order and post-order. Similarly, they ask pre-order. Pre-order means what? Pre-order says first root, then left and then right. So if I follow pre-order, what is the answer? If I follow pre-order, first pre means what? First root. Root is 8. Then left subtree. Again in the left subtree, because you have to apply the recursive approach. So again 3. Then root is over. Then left 1, left subtree is over. Again go to right subtree. Again in the right subtree apply the same formula. Root 6, 4 and 7. So this is the left subtree. Similarly right subtree. If you come to right subtree, again apply root is 10. Then left is not there. Then come to right subtree. Again in the right subtree apply the formula, same 14 and then 30. This is the pre-order traversal for the given data. Similarly, post-order. Post-order says left subtree, right subtree and then root. So you have to follow in this way. So for right subtree means for post-order, what is the answer? The post-order answer is the root will be coming always last. First left subtree, then right subtree and then root. So if you apply post-order, what is the answer? First left subtree. In the left subtree, go to leftmost first, 1. Then right subtree. In the right subtree again left and right. Left is 4, then 7, then root 6 and then 3. So this left subtree is over. After left subtree again go to right subtree. In the right subtree there is no left. Again right subtree. Again left 13. Again it's root 14 and then it's root 10 and then 8. So 8 will be coming always last. In the post traversal, the root will be coming always last. So this is the way you can construct a binary tree and you can traverse. Because most of the time they will ask, after construction of the tree, what is the pre-order, what is the post-order or what is the level order. They will ask this type of questions. Now, let us construct one more binary search tree. Assume this is the given sequence of data. Using this given sequence, you have to construct a binary search tree. Now, always which one you have to decide as a root? The first data is always root. Because in binary search tree, the root is the starting point. So, after deciding root, then you can decide the remaining data, whether left side or right side, based upon the value. Now, after 25, the next data is how much? Next data is 15. So, 15, where you have to insert? Whether left or right? 15 is less than 25. So, left of 25. Next, 50. 50 is greater than 25. So, right of 25. Next, 10. 10 is less than 25. So come to left, and after left there is a 25 is there. So 10 is also still less than 15 left. Next, up to 10 over. Next 22. 22 is because you have to start checking from root. Less than 22 but greater than 25. So right of 15. Next 35. 35 is greater than 25. So right of this 25 but less than 50. So left of 50. So 35 is over. Next 70. So when 70 comes, because you have to start checking from root. My root is 25. After 25, because my 70 is greater than 25, go right side. But after going right side, already there is a value called 50. But 70 is still greater than 50. So go right of 50. So simple. Similarly 4. 4 is less than 25, less than 15, less than 10. So less than, so left of 10. Next 12. 12 is how much? Less than 25 but less than 15 but greater than 10. So right of 10. So based on the value you can decide. Next 18. 18 is greater than, so less than 25, greater than 15, less than 22. So 18 here. Next is 24. So 24 you have to decide whether left of 25 or right of 25. 24 is less than 25. So it should be in the left subtree. So after coming here left subtree again, 15 is my root. But 24 is greater than. So right side of 15. But greater than 24. So this. 24 is right side of 22. Next 31. 31 is greater than 25. So go right side. But less than 50. But less than 35. So next 44. 44 is greater than 25. That means right subtree. But less than 50. But greater than 35. So come right of 35. So based on the value you have to decide in which side the data comes. Next 66. 66 is less than 70. Similar 90. 90 means which is greater than 25. Go right side. Greater than 50. Greater than 70. So right of 70. So this is the way the data will be stored in the binary search tree. Now they may ask a question, what is the level order for this? So the level order is, because most of the time they'll ask what is the level order traversal for the given tree. So you can say level by level. 25, 15, 50, first level, second level, next 10, next 22, next 35, 70, next this level over. Because you have to print level by level. Next 4, 12, 18, 24, 31, 44, 66 and 90. So this is the level order traversal. Now they may ask a question, what are the leaf nodes in this tree? So the leaf node will be always at the bottom and there is no more child. So here 4 is the leaf node, 12 is leaf node, 18 is leaf node, 24 is leaf node, 31 is leaf node, 44 is leaf node, 66 is leaf node and 90 is leaf node. So they may ask a question, after construction of the tree, how many leaf nodes are there? Then your answer is 1, 2, 3, 4, 5, 6, 7, 8. There are 8 leaf nodes. 8 leaf nodes. And how many non-leaf nodes are there? And the remaining are non-leaf nodes. 1, 2, 3, 4, 5, 6, 7. So 7 non-leaf nodes. Non-leaf nodes. And they may ask a question, what is the height of the tree? This is the 0th level, this is the 1th level, this is the 2nd level, this is the 3rd level. So height is 3. So after construction of the tree, you can decide what is the height, what is the leaf, and what is the non-leaf. So without construction, you cannot do. And moreover, they will not give the tree directly. They will give only set of values. So based on the value, you have to construct a tree. Then you have to decide which is leaf and which is non-leaf and what the height. Similarly, you can do the deletion operation also. While deleting a node from the binary tree, there are 3 cases you have to remember. Whether the node, whichever node you want to delete, having no child or having 1 child or having 2 child. Because deletion also possible in a binary search tree. But before deleting, you have to decide what type of child that is or what type of node this is. Whether it is a node with 0 child or node with 1 child or node with both child. That means 2 child. So based on the type of node, the deletion process starts. Now, while deleting, you have to check what case it is. First check whether root is null or not. If root is null, then you can say there is no node, you cannot delete. If the value is whatever the value you want to delete, then from where you have to start? Always you have to start from root. So I should go left of the tree or right of the tree based upon the value. If the value is greater than right, means greater than root, then I have to go to right subtree. So recursively I have to go on if it is greater. If the value is less, then recursively I have to go to left subtree. Then whenever it is equal, then I have to decide what type of node that is. Whether it is a 0 child or 1 child or 2 child. So there are 3 cases for node to be deleted from the binary search tree. Now, after that, once the position is identified, then you have to go for in-order successor of the root if it is a 2 child case. If it is a 0 child, simply delete it and assign to the parent to null. If it is 1 child, assign its child to parent. So, replace this process until you reach the destination. So, this is the step you have to follow while deleting the node. So, these are the 12 steps you have to follow. And finally, replace the root by its in-order successor. And now, recur the right subtree if the new root is found. And finally, return the root node. So, you can go through these 12 steps for deleting the node. Now, case 1, 0 child case. If it is a 0 child case, then find the position and free the node. After freeing the node, assume always the root node will have a 2 child, left child and right child, or any node. This is my left LC, this is my RC. LC always holds address of left child. If you want to delete this node, then go to its corresponding pointer and put a null value. Put a null value and free this area. If it is a 0 child, this is simple. Simply free the memory, go to its parent and assign to null. So, go to the parent and assign null value to the corresponding pointer. Because in every node there will be 2 pointers. Left child pointer and right child pointer. If it is a left child, then assign null to left child pointer. If the node is right child, go to your parent. In the parent, in the right child, put a null. So, based upon the type of node, whether left or right, go to the respective pointer and assign null value. For example, I want to delete 7. This is a given tree. When a tree is given, now you have to find where the 7 is there. 7 is less than 8. That means in the left subtree. 7 is greater than 3, right subtree. 7 is greater than 6, right subtree. So 7 found here. Now if you found here, the 7 having no more child. So that means 7 comes under 0 child. So whenever you are finding 0 child, go to your parent. Who is the parent of 7? That is 6. So in the 6, you are having LC and RC. LC means left child pointer. RC means right child pointer. As 7 is the right child of the 6. So go to parents right and put a null value. So it says that this child is detached from the parent. And that whatever the memory allocated for 7, that you have to free up. So that area is deleted and the 7 is also deleted from the tree. So this is the way the nodes are deleted. 0 child. Similarly, assume you want to delete 7. Yeah, after deleting 7, this is the final tree. So after 6, there is null. So there is null. So this is the original tree and the final tree. Because now 7 is no more. Similarly, deleting with 1 child. Find the node to be deleted using the search operation. After finding the child, then you have to find where the position of child. Because 1 child means what? This is the parent. from parent, there is, assume I can say grandparent and parent, and this is child. If you want to delete this node, that means having one child. After deleting this node, this child, where it has to be there. So you have to attach this child to this grandparent. So this can be deleted. After assigning this child to grandparent, then you can delete. So this is the process you have to follow while deleting a single child. Now this is the node you want to delete, P. Now please observe here. Assume you want to delete 10. Now in this tree, 10 is available right of 8. So here. And 10 having one more child. That is 14. That means it is a one child case. If it is a one child case, now you have to take care of its child. So 10's child is 14. So 14 should be taken care by 10's parent. Who is the parent of 10? 8. So 8 having 2 pointer, LC and RC. As 10 is right child of 8, so the right child you have to assign. So this way you are assigning. Fine. So after deleting 10, the 14 will be assigned to 8. Yeah, 14 is assigned to 8. So this is the final tree. After deleting 10. So this is the way you can delete this. Next, delete 6. Another case. Now 6 also left of 8 and greater than 3. But 6 having one more child. So it comes under one child case. It is having one child. So 6 having a child called 4. But 6 is the right child of 3. So whenever you want to delete 6, its child should be taken care by its parent. So this 4 should be taken care by 3. And after assigning this 3, then you can free this area. So finally, my tree will be like this. So after deleting 6, the 4 will be taken care by 3. So that means the 4 will be right child of the 3. So this is the way you are able to delete this. Similarly, deleting a node with two children. This is one of the little bit tough process. You have to find out where the child available, whether it is having 2 child or not. If it is 2 child is there, you have to find its successor. Another successor or another predecessor. Both are where there. There are 2 ways are there. Either find leftmost element of the right or rightmost element in the left. After finding the child position, you have to find whether you can come left with maximum or right with minimum. Whichever node you want to delete, you find either left with successor or right with successor. Leftmost element or rightmost element. Now, I want to delete 3 from the given tree. Now, if you observe here, 3 is left of 8, but 3 having 2 child. So that means this comes under 2 child case. If you want to delete 3, so you have to take care about it's both the child, left as well as right. So what I have to do? So for deleting 3, there are 2 ways. Either come to left with find maximum, come to left with to find maximum, or come to right with minimum. So both ways are there. Now I can come to left and find maximum, or I come to right, find minimum. Both ways exist. Now, a node having 3 children, replace it with 4. That means I am going to right and maximum. Sorry, right with minimum. Go right of 3. Go right of 3 and find minimum. Go right. 3's right is 6 and minimum. Minimum is always leftmost. So the leftmost data is 4. This 4 you have to replace there. After replacing 4, this 4 you have to delete because the 4 will be available in the 2 places. So replace 3 with 4 and then delete 4. Yeah. Now 4 is replaced here. And 6. Earlier 6 having 4, that 4 is no more. This area is now freed. This area is free. So whenever you want to delete a 2 child case, you have to find go right and find minimum. Go right and find minimum. So that data you have to replace with there. This is the way you have to. Okay. Similarly, if you want to delete 8. Now 8 is my root itself. So find its either right minimum or go left and find maximum. In the previous case, you have seen go right and find minimum. Now here, go left and find maximum. Go left 4. Maximum will be always right side. So go to rightmost. So the rightmost is 7. So this 7 you can replace with the root. And the 7 can be deleted. So now this 7 is kept here. Now this area is, earlier it was 6, right? So now this is deleted. This area is free now. So this is the final tree. So this is the way you are able to do this. Okay. And there are different variations of binary search trees are there. Because to balance the tree, in terms of height, there are 2 trees are there. One is AVL tree, another is red black tree. So to make the operation to be very fast, like insertion, deletion operation, make it very fast, you can go for AVL tree as well as red black tree. These are the 2 different variations. Okay. Thank you. So this is the way you can do it. So remaining thing we'll see in the next session.
Like, share and subscribe. Hit the bell icon for more updates.